Good morning, friends. I welcome you all for today's session. In today's session, we'll be starting with module number 5, this columns and strain energy. Right. So first, let us start with the definition of a column. So a column is defined as a long, slender member with relatively small lateral dimensions. Okay. Now, what does it mean? This word is very important here. Slender. Slender is a word used when the cross-sectional dimensions are very small when compared to the length. So let me draw it and show you if it is something of this sort. Okay, now here what you observe is the length. Let us say this is the length. So if this is the length, right, you can just write here. So this is the length, and you can just check the cross section. So the diameter here will be right. So this is the diameter. So what you observe here is the length is relatively more when compared to the diameter, and such a case we call it as slender. Such a case we call it as slender. A long slender member with relatively very small lateral dimensions. Here lateral dimensions are nothing but the cross-sectional dimensions is known as a column. And in most of the cases, and 99.9% of the cases, the column will always be vertical. Right? If it is a horizontal thing, then it will become a beam. But when it is a vertical thing, we call it as a column, whose length is relatively large when compared to the cross-sectional dimension. Right? So let us see what are the examples where we can call them as a column. So I have listed few examples for you people. The first example is connecting rods in engines, truss members, building columns, etc. Right? So connecting rods in engine, every mechanical engineer knows how a connecting rod looks like in the engine. Right? So you have studied it in your elements of mechanical engineering. You know how a connecting rod exactly looks like. Its length will be relatively more when compared to its cross-sectional dimensions, and that is the reason you can consider it in the category of a column. Next comes truss members, building columns. Right. So for all the buildings, during the construction of a building, most of the buildings, 99.5% of the buildings are constructed on columns. The vertical pillars, what they put after the foundation, so those are called as columns. So if you just observe them, the length will be relatively large when compared to its cross-sectional area. So after understanding what is columns, now let us move on and understand what is the classification of columns. Right? So what is the classification of columns? So columns are majorly classified into three types. Majorly classified into three types. Which are those? Let me check. So the first one is short column. First one is short column. Second one is medium or intermediate column. Medium or intermediate column. And the third one is long column. Third one is long column. Third one is long column. Now, how you are going to classify this? So that classification depends upon the correlation between length and the diameter. If the length of the column, if the length of the column is less than 8 times the diameter, if the length of the column is less than 8 times the diameter, then it comes under the category of short column. If the length is varying between 8d to 30d, that is 8 times the diameter to 30 times the diameter, then that range, if the column is coming, then we call them as intermediate or short columns. If the length is greater than 30 times the diameter, automatically it falls under the category of long column. Right, so the criteria how we are going to decide is the correlation between the length and the diameter. Now, there are other two columns where I have mentioned as compressive stress and buckling stress. Direct compressive stress and buckling stress. Now what are these kind of stresses? So in order to explain that, I need to draw a column. So let me draw a column. So let us say this is a column, and let me say at this end it is fixed. Right. So let me fix it at this end. Okay. So if it is fixed, and here let me join this. Now I'll just mark a line which is a center line for this. So let me mark here. Right. So let us say this is the centroidal axis or the central axis. Right. Now what is happening along this central axis? If I load the beam along this central axis, if I load the beam, so let me load the beam along the central axis. So let me say I'll be using red color. Okay. So let us say this is the point where the load is acting along the centroidal axis. So this is the direct compressive load. Now because of this, what is happening? Two things are happening. And because of this, the entire column is getting compressed, as well as it will buckle. What is buckle? It will bend. So that bending I'll show here. This will be something like this. The column will be bent like this, right? So the diagram may not be that accurate, is pardon me for that. So this will be the final shape. The red colored thing will be the final shape. So two things are happening here. Compressive stress is also compressing or crushing the column, and it is also going for the bending. Right. So two things are happening. Right. Compression is happening, and also bending is happening. Compression and bend both are happening. Now here, which is prominent or which is dominant in which case? So in order to know that, if there is a short column where length is less than 8 times the diameter, for short columns, direct compressive stress will be dominant or it will be significant. Direct compressive stress will be dominant or it will be significant, whereas buckling stress, that is the bending stress which is coming here as a result of this applied load, will be very, very negligible. It will be very, very negligible in case of short columns. Next, if I consider the same thing as a case of medium or intermediate column, then here for this kind of column, both are significant. When I say both are significant, both are going to have an equal contribution almost, and we need to consider both of them. In the first case, since the buckling stress is negligible, you can neglect this stress, and for short column, you can only consider the direct compressive stress as the stress which is coming on the beam, right? Vertical beam or column. Next, the third case is for long column. For long column, it is the other way. Here in this case, the direct compressive stress becomes negligible and the bending stress becomes more significant or dominant. Right? For long column, bending stress is more dominant, and that is the reason we'll consider only that particular stress, and I'll directly neglect the compressive stress. So here, this table is very important for you people. So you need to thoroughly remember this table in order to understand the entire concepts of columns. Right. So that is one important thing. Next will be moving on to the next important topic. So before I go to the next important topic, that is Euler's theory, let us understand some terms. So first very important term which we'll be using every now and then in the chapter of columns is slenderness ratio. Slenderness ratio. Now what is the slenderness ratio? It is the ratio of length. It is the ratio of length to least radius of gyration. Ratio of length to least radius of gyration. It is very important. Least radius of gyration. It is not just radius of gyration. Least radius of gyration. Right. So its value for short columns is less than 32, and for long columns is greater than 120. And obviously for intermediate columns, it ranges between 32 to 120. It is ranging in this one. So slenderness ratio is denoted by ES. It is the ratio of LE. LE is effective length of the column. So what is effective length, that I'll be telling you in a while when I'll be encountering with this term once again in the next session, that is in the next video. For time being, you just know it is a type of length which is associated with the column. And K is least radius of gyration. Right, so slenderness ratio is very important for every column what we are going to study hereafter. So you need to know that it is the ratio of effective length to least radius of gyration. Next very important term which is used frequently is factor of safety. Okay, so factor of safety, it is defined as the ratio of critical load to safe load. Critical load to safe load. Okay, so this is used for designing of columns. So further we'll be seeing some numericals where we'll be designing the columns, we'll be deciding the type of load which will be coming, maximum load, minimum load, all those things. For that we'll be making use of factor of safety. So factor of safety is the ratio of critical load to safe load. Next important concept comes is the stable, neutral and unstable equilibrium. At what kind of equilibrium we are going to decide depending upon the load that is being applied. Right, now here let us first study regarding stable equilibrium. Now for showing stable equilibrium, I have considered a column. This is the column. It is subjected to certain load P which is less than PCR. PCR is critical or crippling load. Crippling load. Crippling load. PCR is crippling load. Crippling is nothing but load required to bend the column. Right? So P is less than PCR. Sometimes it is also called as critical, sometimes it is called as crippling load. Right? So PCR. So this is the term which is coming in Euler's theory, which we'll be studying in a while. So P is less than PCR. In this case, when the applied load is less than PCR, then the body or the column will be in stable equilibrium. The body or column will be in stable equilibrium. So here the beam will be subjected to compressive stress. Here the beam will be subjected to compressive stress. So that I have shown here, compressive stresses. Beam will be subjected to compressive stresses. Next, in the second case, so what we are having in the second case, P is equal to PCR. So you can just check here, P is equal to PCR. So when both are equal, the applied load is equal to the crippling load, then the stable equilibrium will be shifted to something called as neutral equilibrium. That is intermediate. It is not neither completely stable nor entirely unstable. It is in between. It is neutral. Right. So the beam almost remains straight even after the application of load. Here the beam almost remains straight even after the application of the load. So this is important. So beam remains straight even after the application of the load in the second case. And now we'll go for the case number 3, that is P is greater than PCR. So what happens if P is greater than PCR? If the applied load is greater than PCR, if the applied load is greater than PCR, then obviously the beam will bend. So that is what I have shown here. The vertical beam or the column, it has bent. Right? Why it has bent? Because the applied load is greater than the crippling load. Right? So P is greater than PCR, and that case it is called as unstable equilibrium. Unstable equilibrium, and the beam is subjected to buckling. The beam is subjected to buckling stresses and is bent after the application of load. Now here there are a few important things which you need to note. First one is, whenever I call it a stable equilibrium, just to make you remind things, I'll be using this example. Ball in a cup. So you are having a hemispherical cup, in that you are keeping a ball, so the ball will remain stable. So this is an analogy which is depicting the stable equilibrium. Right? In the second case, you are having a flat plate at the end of which you are keeping the ball, so it is in neutral equilibrium. And at last you are keeping an inverted cup, on that you are keeping the ball. It may roll down anytime. That is the reason I call it as unstable equilibrium. Right, here it is exactly at the center, so it is stable equilibrium. So these are the 3 cases which you need to thoroughly understand. Next, with this backdrop, I'll be moving to Euler's theory. Euler's theory of bending. So Euler is a scientist who gave us the theory for bending. So Euler considered bending of columns as the direct compression due to load applied So here there is a requirement of a comma or a pause. I'll just write here. Euler considered only bending of columns. You just put a comma over here. Just put a comma. As the direct compression due to load applied was negligible when compared to bending or buckling. And what he is trying to tell here is he has considered a long column. So if you remember the table which I gave you, in that long table where I have listed the long column, I have clearly specified that for long columns, only buckling will come into picture and the direct compressive stress is negligible. And that is what Euler has made use. He has considered only the bending of columns. Euler has considered only the bending of columns. He has not considered the direct compressive stress. Direct compression is negligible according to him, and that is the reason Euler's theory is only applicable for long columns. Euler's theory cannot be applied for short columns and intermediate columns, and this is one very important thing which you need to always remember. So before you take up any numerical and start solving it, first check whether the column given is a long column or a short column or an intermediate column. Unless and until you are clear with that, you cannot move ahead. Right? So Euler's column theory is only applicable for long columns. So then there are certain assumptions which Euler made in deriving the equations. So assumptions made in the Euler's theory. So the first assumption what Euler made was axial load is perfectly collinear with the axis of the column. So what does it mean? Suppose there is a column of this sort, right? So let us say this is the column. So let me join this. And if there is some other axis at the center, central axis, so I'll just show it by some other color. Now, axial load is perfectly collinear with the axis of the column. What does it mean? Now, if I just show some load over here, okay, so this is the load. Now, what he is trying to tell you people through the first assumption is this load, whatever I have applied, is perfectly collinear with the axis of the column. Right, so axis of the column is shown in pink color and the load is shown in brown color. Both are collinear. They lie on the same line. So that is the meaning of the first assumption. Next, we'll go for the second assumption. The second assumption is material of the column is homogeneous and isotropic. So this is important. What is homogeneous and isotropic? Homogeneous means it is made up of only one type of material or a uniform material throughout. It is made up of uniform material throughout the structure of the column. Suppose if it is made up of copper, if it is made up of steel, right, any one type of material will be remaining throughout the column. That is, composite columns are not considered in Euler's theory. Right? So if it is a steel material, then entire beam or the entire column which I am considering here is made up of steel only. That is what is the meaning of homogeneous. And isotropic is the value of Young's modulus remains same in all the directions at any point inside the column. Right? So that is the meaning of material of the column is homogeneous and isotropic. Next, material of the column is elastic and will always follow Hooke's law. So what I am trying to tell here is this Euler's theory is studied by loading the column within the elastic limit. Right? The column is loaded within the elastic limit. Then the length of the column is significantly large when compared to lateral dimensions. That is visible here. The length of the column. So this is the length of the column. So length of the column is relatively large when compared to this cross section area. Right? Length of the column is relatively large when compared to the lateral dimensions. So that is the fourth assumption. Next, the fifth assumption is self weight of the column is neglected. Very important thing, self weight of the column is neglected. Since the column is placed in a vertical manner, its weight will be acting down because of its gravity. Because of the gravity, whenever you place any object in a vertical position, obviously its weight will be acting down. While deriving the Euler's equation, Euler has neglected the self weight of the column. That is one of the important assumptions. And at last, the column is straight before loading. Right? Before I could apply the load, the column what I have considered is entirely straight. Right? So that is very important assumptions. So there are around almost 6 assumptions which you need to remember as well as understand, because everything you cannot by heart. So try to understand the concepts and then reproduce it in your examinations. So that's it for today's session. In the next session, I'll be starting with the core part of the columns, that is the Euler's theory, how to derive the Euler's formula for different end conditions, and all those related stuff. So till the next session, have a nice day. Take care. Bye bye.